Welcome back, everyone. So far, we'll get going at just the end of the minute. Well, I think we can get started. Welcome back, folks. Thankfully, today, I'm pretty much over that cold I was dealing with on Monday, so I think it'll be kind of a normal class from my end. For today's class, we're going to be working through section 5.3. We're on the second part of example 1. Really, it's all just based off this information here. And next Monday, we're not going to have a class on Zoom. It'll be kind of a day for us to pause the course. We'll be doing our first exam officially on Monday. But like we mentioned, if there's problems with your schedule, testing centers are filling up, you can schedule that for a different day. It can be scheduled for any time of the day, and it's going to be a 50-minute exam. Also, when you're studying for the exam, we mentioned best thing you can do to study for it is complete your sections 5.1 through 5.3. I'm going to begin grading them on Friday's class, and this class will be my priority one for grading. So watch your ISU email or whichever email you sent it to me from. I'll be emailing the feedback directly back to you. So best thing to do is get caught up on these sections. Then
Even like so this teacher where he goes over basically each module each week we're like working on like 5.1, 5.2, 5.3. And so he's like doesn't want to rush it. And so as we go, he'll
I think that was an open mic. I thought that was a question. Sorry about that for a moment. But other questions at the moment? Okay, other things you might want to take a look into are the sample exam 1 problems, version 1, sample exam 2 problems, version 2. And these will be helpful to give you an idea of what the real exam questions are going to look like. So I make them pretty close to what we do in the lecture notes. Whole purpose of the homework exercise is just to give you that additional practice to prepare you for the exams. So this is pretty much what we were doing last section. We did one evaluation. We're going to practice a bunch more for the sake of good practice. The idea is when we look at the terminal position of the angle theta, sine and cosine are defined to be the second coordinate y, first coordinate x for sine and cosine. But now tangent is sine over cosine, and that's the new function. There's 6 in total, so a lot to memorize. But on the right-hand column of this table here, we're just literally taking the reciprocal of what you see on the left. So cosecant is 1 over sine, secant is 1 over cosine, and cotangent is cosine divided by sine. So our whole goal is just to practice those and doing the evaluations as we go. Before we launch back in, any questions at the moment? Okay, well, here's where we left off. We finished off the tangent 11 pi over 6. We found the terminal position. We pulled the coordinates and we just said tangent is sine over cosine. Working it out, the actual arithmetic here is more involved, it looks like, but on paper, than doing the trigonometry, which is over here with the color coding. I mentioned this table right here is provided on the exam, so we'll be walking through these problems carefully using that table as we go. So here's our second one for the day to start us out. We need to get a position on the angle, -3 pi over 2, so that's possibly the first thing we do. Here's the not quite good sketch. Let me try again. Oh, the circle is good. Control Z went a little too haywire there. Now the angle, because it's negative, we'll say put a -pi over 2 here, going the clockwise direction. -3 pi over 2 is over here. And the coordinates at that point would be 0, 1. So now that we have that, we can say, well, secant is going to be 1 over cosine. You could either put the -3 pi over 2 there, But you'll notice that this is also the same terminal angle as pi over 2 and the same exact coordinates. So up to you if you want to keep negative 3 pi over 2. I'll keep it in for the notes. But if you put in pi over 2 and you're looking at this part of the table, that would have been just fine as well. But notice the problem. Cosine at that terminal position, whether you think of it as a negative 3 pi over 2 or positive pi over 2, cosine at that angle measurement is 0. So this is now 1 over 0, and the whole thing is undefined. It deserves an exclamation mark in this problem. And that's something new that happens, not with sine or cosine. Those always had an output to every single real number input you put inside here. But once you start defining the reciprocal functions, or the tangent, sine over cosine, the moment something becomes 0, we have undefined. So now we have domain and range type issues that are coming into these kind of problems. And we'll be looking into more of those when we start plotting the functions in the next chapter. But one thing to be aware of, you'll see this in the homework as well. Sometimes things are just flat out undefined. So this is the answer we would have to give. Well, that's one down. Any questions at all, folks? Getting part B down? Okay, let's try out another one then. Let's put this maybe on the next page so we're not cramming it in. Cosecant 5 pi over 6. So again, if you're doing this on exam 1, you might have to flip back a page, but it's going to be there somewhere inside the exam, this table. Probably already you've drawn a unit circle. If you have, good on you. If you can visualize this really well, like I mentioned, then this might not be necessary. But for most people studying trigonometry for the first time, this is a good start. So next thing we'll put down is this angle pi, which we've used this trick before, is 6 pi over 6. It helps us see right away that 5 pi over 6 would be that measurement right there, just 30 degrees short of the half rotation, 6 pi over 6. Then from then on, next thing we have to decide is what coordinate do we actually need? The reference angle on this one is the pi over 6 due to that denominator 6. And so this is the other new bit of information. We need to know, think back on the table that we had on Moodle or at the very top of these notes, if cosecant is 1 over sine or 1 over cosine. Anyone happen to recall which function would go down here?
Sine would go down there.
Yeah, absolutely. Thanks, Kai. So sine goes into the denominator. We say sine 5 pi over 6. And at this stage, now we know which actual angle that we're going to be using. We're using the, not angle, what coordinate we're going to be using. We're using the second coordinate of exactly 1/2. Notice that appears here. The only danger is it could have been negative 1/2. But terminating in quadrant 2 for sine function gives us positive. So now this is 1 over 1/2. This one simplifies really fast. The reciprocal of 1/2 is just 2. And our work is totally complete on that one. So that's what evaluations look like for all these kind of problems. Yeah, go ahead, Luke.
Why would a negative 1/2 be a problem?
Oh, it wouldn't have been a problem, but if it was, say, the only problem would have been is if it was this angle right here. Let me draw it a little bit better so it's not. There we go. If it was, say, a 7 pi over 6, that's the one to watch out for, because then cosecant 7 pi over 6, following the same method, is 1 over sine 7 pi over 6. We're looking at the same exact reference angle right here, but this time it's not going to be the positive 1/2. We would take this coordinate right here, which is negative 1/2. So it wasn't so much of it's a problem, or it's more something to watch out for. It's either going to be positive 1/2, or like in this case, a negative 1/2, giving a negative 2 as an answer.
Oh, okay. So it's not so much a problem with having an undefined 0 in the denominator, it's just having a sign switch up.
Yeah, we have to watch out if it was 5 pi over 6 versus 7 pi over 6. whether we're getting the positive or the negative answer exactly.
Okay, thank you.
Yeah, thanks for asking about that. Other questions at the moment? Move that table down as we go. Okay, here's our next victim, secant 5 pi over 3. I'll put the unit circle here so it just doesn't get too busy over there on the right-hand side. Okay, not my best circle of the day, but that'll do the job. Sometimes 5 pi over 3s are kind of tricky, but if you already know what it is, you just want to draw it down. I'm writing these down as we go, just as a way to kind of help show what the steps would look like for memorization. I first put down a pi over 3 here. This one, not drawn too well, is 2 pi over 3. Then down here, this is where we get 4 pi over 3. And the angle we actually want is over here, 5 pi over 3. So other thing we'd look at is the reference angle on this one is pi over 3. So we know we're either using root 3 over 2 or 1/2, but we also have to determine is it positive or negative on each one of these. So next step we take is we can say, well, a secant is, let me just move that pi over 3 so it doesn't get too jammed in there. A secant is 1 over cosine. So this is 1 over cosine 5 pi over 3. Now that we know it's the cosine function, we take whatever value that's going to be, positive or the negative, depending on where we terminate right here. So we terminated now in quadrant 4, and so for quadrant 4, cosine value is whatever this number is on the positive x-axis. So it tells us, well, now this one is positive 1/2. It's kind of nice, it matches up, but like we saw over here in the orange, it doesn't have to. So all this careful work is just to make sure we get the right sign. So here, 1 over 1/2. Reciprocal of that one comes out as a 2, and then we're done with that one now. Usually the ones that go sines, cosines, cosecants, secants, they go pretty quickly. The tangent cotangents sometimes have a little bit extra algebra to run through, so those might take you just a couple more steps to simplify. But that's our part D on that one. Any questions so far, folks, running through any of these? Okay, let's practice some more. Tangent negative pi over 2. Looks like we have several more to take a look into. I mean, that's just as well. This is good practice. This is possibly a pretty new way of computing things, depending on how familiar you are with this kind of stuff. So tangent negative pi over 2. First thing we want to do is, well, a couple things you might want to do. First thing I would usually do is put the angle down. So let me start by doing that. Once I can get a good circle going. You don't have to be too picky. The negative pi over 2 is down here. And coordinates at this location would be 0, -1. These ones are not too bad to just drop in the coordinates if you preferred. We just have to be careful with tangent. We did mention there's kind of a nice little mental trick with this one. If you're dealing with a cotangent of some angle theta, the fact that it starts with a co right here is a giveaway that the numerator should be cosine of that angle theta. So that's a great way to kind of memorize how cotangent goes. Then the good news with this trigonometry stuff is if you've got cotangent down pat in this way, kind of a nice parallelism there, then tangent is just going to always be the reciprocal of cotangent. So that means flip this whole thing. Sine goes in the numerator. Sine negative pi over 2. Cosine goes in the denominator, so cosine negative pi over 2 down there. And now we're on our way. So we just grab the coordinates. Sine is going to be the second coordinate, cosine is going to be the first coordinate. And sometimes these are a little bit frustrating because you might have noticed, maybe you already saw it at the very beginning. If so, good on you. But sometimes you do a whole lot of work and then you discover in the end, the whole thing is undefined once again. So only due to the 0 in the denominator, this is undefined. And we just stop on this one. Any questions with this one before we try out part F? Okay, maybe for the sake of just adding a what if to this, what if it was cotangent negative pi over 2? If it was this version, we would have used cosine negative pi over 2 in the numerator, sine negative pi over 2 in the denominator. This time when we pull coordinates, cosine goes into the numerator, so the first coordinate. Sine goes in the denominator, so second coordinate -1. This one is defined. 0 divided by anything is just 0. So cotangent at negative pi over 2 is totally fine. It's just 0 exactly. But you cannot take the reciprocal of 0 whatsoever. And that's why tangent at negative pi over 2 is the one with the problem. This is the one that was undefined. Anything in orange is just for extra information, anything extra for the notes. So it's good to see sometimes new scenarios, kind of like how there's a question about the cosecant 7 pi over 6. But always try to make the official answers in black, so these seem more like just side thoughts. So here's one last one, cotangent negative 7 pi over 4. We can probably leave the table down here. Like before, depending on how you decide to compute this, we're just going to first go to the unit circle. That's a pretty shoddy looking one, but it's only just to contain information. It doesn't have to be perfect. Starting at here, this is now negative pi over 4. We're going in the clockwise direction. These go by odds in the directions we're plotting. So this is now negative 3 pi over 4. Up this way, negative 5 pi over 4. Finally over here, we end at this one, negative 7 pi over 4. And let's emphasize this comment once more. Negative 7 pi over 4 is the same terminal position as pi over 4. That means any one of these trigonometric functions we've defined at one angle or the other is going to be completely the same. If you wanted, you could rewrite this and just say, this is the same exactly as, let me try again, cotangent pi over 4, and that would have been just fine because they terminate at the same exact position. On the other ones, we left it negative 7 pi over 4, but let's leave it this way on this one just to emphasize that's a completely fine way to go. Here, you might have already spotted the answer because cotangent is just cosine pi over 4 divided by sine at that same angle, pi over 4. But this time, we're using the dead-on angle right here on the table. And even if we take the extra step to carry in the information, it's now just identically equal to 1. Let's do it just for emphasis. The cosine is root 2 over 2. Sine value is identical, root 2 over 2. So this one comes out as exactly a positive 1. Cotangent or tangent at any odd multiple of pi over 4, so 3 pi over 4, 5 pi over 4, negative 7 pi over 4, is either going to be a positive 1 or a negative 1. It just depends on where you're terminating on the unit circle. But we did it, folks. That's a quick rundown of doing trigonometric function evaluations. And the homework for section 5.3, it looks like it's really, really long, loads of problems. But in fact, all it is a sequence of doing these kind of practice problems. The homework set is shorter than it actually seems when you look at that long list of problems. In fact, I'm going to try to keep all the problem sets about the same length to the best of my ability. So sometimes if it seems like there's only very few problems, that means they probably take a lot of extra steps to get through. If there's loads and loads of problems, that might mean this because they're all really fast to get through. But this was the fundamental big set of problems that we need to be ready for on the upcoming exam 1. Any last questions or comments before we look at a couple of additional topics in 5.3? Okay, so the last part of section 5.3 is really just dealing with a couple extra properties of trigonometric functions. So we're going to deal with odd functions and even functions. Then coming down below, this is just a set of quick concept type questions. I believe there's something pretty similar to this on the first exam as well. So we'll show how something like this goes. Then we're rounding up some more identities. This is the original Pythagorean identity. The two other ones are bonus identities that we get once we define the other four trig functions. And even though this one, I should say, just because we're getting close to the exam, this one's not on exam 1. I don't think I assigned it as a homework question either, but it's an important question for practice, so we'll try to get it through today. If we run out of time, then it won't kill us. We'll come back to this after the exam. So let's go back to even and odd trigonometric functions. This is now kind of a good set of review from the Pre-Calculus 1 course, sometimes called college algebra material, when we were just first dealing with functions themselves. So we defined even functions. Even functions are symmetric about the y-axis. So for example, like y equals x squared is symmetric. And then so-called odd functions are symmetric about the origin. You know, it might help to have a little demonstration with that just to get a feel for what's going on. Let's actually take a look at these functions plotted. I had this open before class started and I didn't think I needed it, but here we are. Turns out we do want a calculator for this. Not that a calculator is ever required on the exam, just to illustrate the concepts. So our told even function has this property, f of negative x is f of x. And y equals x squared is an even function. So here's y equals x squared. And here's the property. It's symmetric about the y-axis. You can fold the paper across this axis here, and the curve lines up. The definition also goes on to say y equals x cubed is an odd function, and that's the equation that goes along with it. So change the power to 3, and this is what we mean symmetric about the origin. If you fold this point once across the y-axis, fold it again across the x-axis, you end up on the same point on the other side, opposite quadrant. It's symmetric about the origin because the origin is the only point that never moves when you do the two reflections across both axes. So that's what odd functions look like. Then out of the blue, we're told cosine is an even function, sine is an odd function, meaning they would have those properties here and here. The next chapter is all about looking at graphs of sine and cosine, but it wouldn't really hurt to take a look at that right away. First, this is what an even function looks like. We're told cosine is even, so it has to have some property like this, symmetric about the y-axis. So here's cosine x, and it does in fact have that property. It has this nice shape here, giving it symmetry across the y-axis going that way. Does that make sense to folks so far on cosine being even? Okay, we're also told sine is an odd function, so it behaves like y equals x cubed. Here it is, just as a refresher on our mental blackboard on that. So somehow sine has this kind of property. Let's put sine on the graph. Sine x looks like that. A little bit more complicated than y equals x cubed, but this whole graph turns out to be totally symmetric across the origin. So if I take this point, flip it across here, flip across the x-axis, I get back to this point. It says sine of negative theta is negative of sine theta. And that's why we're seeing these coordinates come out as opposites, or the second coordinates, 1 and negative 1. So this is just giving us one way to think about this, relating pre-calculus 1 material with this quadratic and that cubic function. But in a certain sense, it's almost not fair because we haven't looked into graphs really just yet. That's chapter 6. So we will explain why cosine is even, why sine is odd, using nothing but the unit circle. So that's the whole purpose of exam 2, or example 2 rather. Not a good exam problem, but really just for the sake of getting used to these two formulas here that are color-coded. First thing we need is a really believable unit circle. So I need a best attempt at a circle this time. That's not too bad, actually. I'm kind of proud of myself. And then I messed up on the straight line. There we go. So here's our unit circle, x squared plus y squared equals 1. I need an angle theta measurement, and it can terminate anywhere here on the unit circle. But for the sake of not making the diagram too complicated, I'm going to terminate it right here. Almost looks like a 30-degree angle, but it doesn't have to be. So here's theta. Theta comes up in these formulas. But I also want a negative theta. So we rotate counterclockwise to theta, rotate clockwise to get negative theta. This is make sure you rotate by the same degree measurement, best you can do by hand. And that would be our negative theta down there. Now let's first look into what happens with cosine. I want to do the normal thing, look at cosine theta. And the big punchline to section 5.2, cosine theta, right at this location here where it terminates, is the x-coordinate. And that doesn't look quite believable just yet. Let me see if I can fix this angle a little bit to make it look about the same. There we go. Here's negative theta. My diagram was not looking like it was going to work out. So for an angle measurement negative theta, that seems to be about the same magnitude, but now in clockwise direction. If we go to look into cosine negative theta, it just says go to this position here and go up to the x-axis. I fudged it a little bit, so we have to understand it's not perfect machine plotting, so I made my arrow go just a little bit to the left. If I had a perfect tools, these would always be exactly the same position. But all that's telling us is that this one's cosine theta. This one is cosine negative theta. They both hit the same exact spot on the x-axis, so they're equal to each other. That's all this equation is trying to tell us, but look how fantastic that is in a way, because it means if you don't like dealing with the negative angles, and we dealt with a few up above on those notes, you can full on just delete it, and you're doing cosine of the same exact value. Your outputs are always the same. So that's what an even function gives to us. And that's why knowing cosine as even function is really valuable. This is just one way to explain it through the unit circle. Well, any questions, folks, with the explanation for cosine itself? Okay, same sort of explanation for sine, but usually odd functions are a little bit more complicated. Look what happens with the negative sign on the odd function. It doesn't get eliminated. It moves outside the function and becomes a constant multiplier. These are pretty interesting properties, and they can be useful in a lot of surprising ways. Here's what it would look like on the graph. So first I'm going to focus on this angle by the red dot, sine theta. The sine theta value would be on the y-coordinate somewhere right here. So this location is sine of theta. Ignoring the negative sign for the moment. Now I'm looking into sine negative theta. That means go to this terminal position on the unit circle. Y-coordinate is now negative, and this position here on the y-axis is sine negative theta. And notice they're about the same distance away from 0. One is just the opposite of the other. That's what this is saying. Sine of negative theta is just the opposite of sine positive theta. So we can say here, this equals negative sine theta. In other words, if you put a negative sign on this, it would reflect across the x-axis and end up in that same exact spot. So that's the whole big punchline to the cosine being an even function, sine being an odd function. Its immediate use is going to be in chapter 6, its big use rather, when we go to use that to start plotting the sine functions and the cosine functions. But for the moment, it's just a useful identity that you could take advantage of if you'd like. In other words, if you ever had to calculate sine negative pi over 3, what this is telling us is that it's just the same as negative sine pi over 3. Then you could go up to this table here. At pi over 3, sine is root 3 over 2. And just say the whole answer is negative root 3 over 2. So if you really want to, you never actually have to plot a negative angle. You can just use these little tricks to pull out the negative sign, or for cosine, just eliminate the negative sign outright, and that's completely fine. And use the same table that we're using above to get the values. Well, we'll practice a couple more problems along these lines, but any questions at the moment? Okay, this last question here is pretty much the end of the exam 1 content. It's all about the various formulas that we've been dealing with so far, the even function, the odd function, as well as the Pythagorean identity. We'll need this one as well, which says sine squared theta plus cosine squared theta. Let me fix that. Equals 1. So this one's a really fast kind of concept type question. And here's how it goes. It just tells us if cosine at some angle t is 0.87, what is the value of cosine negative t? Really, we're just using the fact that cosine is an even function. So we can do this whole problem by just simply saying, well, cosine of negative t is just the same as cosine of t. So the answer is just 0.87. All we used is this formula above to get an answer out right away. So it's just pretty much just a concept question is all example 3 is all about. Some of them get a little trickier, so we'll go carefully on the next ones. But any questions, folks, on part A so far? Oh, that's a great question, Alex. So looking at this again, it says cosine t is 0.87 from this part right here. But the trick with cosine is the formula above is telling us we can pretty much just literally delete that negative sign just outright. So when we came down here to calculate cosine negative t, that's essentially what we did. We put in just cosine t itself. So that was us going from here to here in the formula. But once we're at cosine t, it's really just a substitution, gathering that same exact value for now cosine t itself. However, if we use the sine value instead of cosine, you would have been absolutely right. Sine does include an extra negative sign right here, and our answer would have been opposite. But cosine is different. Cosine is going to give you the same exact value, 0.87, whether you were calculating cosine t or you were calculating negative t. Kind of weird in a way. Yeah, go ahead, Luke.
So correct me if I'm wrong, but does that mean every cosine value is going to be positive?
It does not. Cosine can still take on negative values. All it's saying is when you go to calculate cosine, it doesn't matter if you're doing a t or a negative t, the values would always match up. So maybe another concept to go along with that question as well is this problem could be rewritten as if cosine t equals, say, negative 1/2. And that certainly happens because cosine at, say, 5 pi over 6 is equal to negative 1/2. You know, it doesn't hurt to put in the unit circle diagram. We're still learning that. At 5 pi over 6, we're over here. Oh, hang on, kind of messed that one up. Not quite 5 pi over 6. That one, let's stick with it, is negative root 3 over 2. Kind of is revealed what your mistake is if you go to draw this out. That doesn't even look close to negative 1/2, right? So that's a kind of the good value in drawing these things out. You'll catch mistakes like I just did there. So cosine 5 pi over 6 does come out as negative root 3 over 2. Let's keep that the same down below here just for the sake of parallelism. So if the whole question didn't tell us the angle and it just said t, like it does over here, if cosine t is negative root 3 over 2, then cosine negative t is also negative root 3 over 2 as well, just automatically. It would take on the same exact value. And thinking along those lines, let's take a look at that. Cosine negative 5 pi over 6. So I literally put in the negative value here to match up with that negative t there. Negative 5 pi over 6 has a terminal position right here, same as 7 pi over 6, and will give us the same exact value. Still a negative root 3 over 2. Any questions about these so far?
Thanks for the clarification.
Yeah, absolutely. Thanks for asking about them. There are honestly pretty tricky formulas when you take a look at them. So the more questions asked, I think the better to really get a feel for what's going on. Let's try out the next one. Sine is no easier. This one does have a negative output. It says sine t is negative 1/7. What is the value of sine negative t? So the short of this is you just now change the sign of the output. But the y to that is just as important as the actual answer. So let's write it out. First, do sine negative t. That's the thing we're meant to calculate. Then we use the fact that sine is an odd function. That means this happens. The negative doesn't go away. It moves in front of the function this time. Whereas over here, the negative sign, you're allowed to just straight out delete. That's kind of cool in a way. You can just change the problem. You get the same answer. That's a rare thing in mathematics. But over here, the negative sign moves in front. Now it's just negative sine t itself. Here we want to be really careful when we do the substitution because this part is sine t and its output is negative 1/7. So now we have a negative from the one we pulled out right here, an extra negative sign from the substitution, following the yellow color coding. So this one turns out to be just a positive 1/7. So in other words, if you move from an angle t and you make that angle opposite, the output, whether it was positive or negative, will change signs. Ours went from a negative sign to a positive sign on this example. Does that make sense to folks on how the sine one's going? Okay, let's try out another one then. This one almost seems like it's unfair in a way because the book only gave us information for even and odd on two functions, cosine and sine, and yet now we have a cotangent. So what we want to do on this one to get a feel for what goes on is take cotangent t, and the good news is doesn't matter what trig function we're being given, information on cosine and sine tells us everything we need to know because all of the other functions, if it's not a cosine sine, it's built from cosines and sines. Cotangent is a cotangent t divided by sine t. So we can use that property there to help us along. What we want to evaluate is cotangent negative t. So let me put a little border here. Yeah, go ahead, Luke.
Don't you mean cosine t over sine t, not cotangent?
Oh yeah, absolutely. Good eye on that one. I was getting really happy with the cotangent there. Yeah, thanks for spotting that. Cosine over sine.
That would have been kind of weird to evaluate cotangent by using itself.
Right, that would be kind of an amazing equation to find an angle that works there.
That's like computer code when you're doing math operations and then reassigning it. You would
Persian,
put the
yeah.
variable and then you variable plus whatever. It kind of feels like the same thing here. But
Yeah, I
that
agree.
doesn't work.
So with the actual cosine, not self-referential cotangent once again, let's now go back to cotangent negative t. That's the one we actually want to calculate. And now carefully, cosine negative t is what's going to go in the numerator here. divide by sine negative t. We're still have issues, right? We have negative angles. We don't know necessarily how to put them together, except that we have properties above that helps us. So for the property in the numerator, we straight out literally eliminate the negative sign because cosine is even function. That's powerful once you really do it by hand and appreciate what you just did there, just deleting a part of the problem we didn't like. Then across the denominator, we can't do the same thing, unfortunately. That'd be amazing if we could do both for sine. But all sine does is it takes the negative you see there and spits it outside of the function. So it's -1 times sine t. Negative sine t is just the abbreviation for that. It feels like we're still stuck even when we get to this point. But you can start putting this together. This is kind of an optional step just to visualize. Let me move the negative sign out so it's not a distraction. It's cosine t divided by sine t. Let me fix that c there. But once we get to this stage, recall cosine over sine. Same exact formula over here, we're just going backwards, is cotangent. So negative copies in. This is now cotangent t. And we're in good shape now. We're told cotangent t itself is 4. Here's cotangent t. So following the yellow color coding, we just literally put in a 4 there. The output is -4. So it turns out what happened was we just changed the sign of what we had here to a -4. If you see that that's coming already, that would have been just a fine shortcut. And this one is really more for the sake of just extra practice with these above, honestly. For the real exam questions, I'm not going to throw anything with too many steps. I can't have a long exam. So this one was more just for fun and part C. Well, major ones you should look out for on the upcoming exam are the concept questions, parts A, parts B, as well as part D. Any questions at all first on the part C version? Okay, now part D almost looks unfair in a way. Exam 1 is closed calculator. We're only going to be giving exact numerical values for all of our problems on exam 1. And now you're being told calculate sine squared 3.4 plus cosine squared 3.4. And it might seem kind of unfair on paper, but does anyone happen to know what the exact value of that is just by looking at it? I'm going to throw down a formula just in the corner for inspiration while we're looking at this one. So this is our Pythagorean identity on the bottom left corner right here. And what makes this problem pretty tricky is I didn't give you theta. I just gave you a particular value for theta. Theta is 3.4 on this problem. And down below, this is what it looks like as an identity. It's telling us that sine squared theta plus cosine theta is identically equal to 1 for all values of theta whatsoever. But somehow when you go from a theta to a constant value like this, sometimes it feels a little kind of foggy of what we're really meaning. But it's the same exact thing. This one is still exactly 1. Doesn't matter if we put the angle theta there. Doesn't matter if we put in constant numbers. What does matter is if I did 3.1, now that's a huge problem. The exam problem is flawed. You'd have to have a calculator to compute this. This is no longer exactly 1. Critical thing is you have to have the same exact angle theta here, same exact angle theta here. This one just happens to be 3.4 radians, 3.4 radians. So watch out for this one. This one can be kind of nasty if you've never seen it before, because usually we're thinking in terms of the analytic formula, not always what it would look like with an actual constant thrown in. Well, that's the conclusion to the example 3 problem here. Any last questions or comments, folks, before we take a look into the next content? Okay, for the sake of notes, well, really for the sake of studying for exam one content ends here. And so does the homework problems. I didn't want to go look too far, but I still have a little bit more in the notes that I want to take a look into. At this stage, you can complete all the homework problems so far. And this is the other thing I wanted to just take a look into before we fully closed out these notes. So it's the Pythagorean identities again. The first row is the one we were just looking at. Sine squared plus cosine squared equals 1. Example 4, just to emphasize again, is not on exam 1. But these are two additional identities that seem to come out of nowhere. And the further we get along throughout the book, particularly in chapter 7, these start to take a lot of great importance. So this is kind of our first look into these sort of identities. With the remaining time we have, let's look into deriving one of them. And when we come back on Wednesday after our exam, we'll be finishing off example 4 and moving into section 5.4. But let's take a look into just deriving one of them to give some sense of what's going on. So the way we prove that these identities are true is we start with the original one. Sine squared theta plus cosine squared theta equals 1. So this one is just a consequence of how we define the unit circle. X is cosine, y is sine, and the unit circle is x squared plus y squared. So it's just saying the unit circle equation in a slightly different way, emphasizing the trig functions. But now if you want to derive row 2 tangent squared, all you do is this interesting step. Divide by cosine squared theta here, cosine squared theta here, and cosine squared theta here. If you did that, sine divided by cosine is a tangent squared. Cosine squared divided by cosine squared is exactly 1. And 1 over cosine squared is secant squared theta. And that immediately proves this identity right here. If we divide by sine squared instead, we would have gotten the third row instead. So we'll look into more on those 3 different identities altogether when we come back on Wednesday next week. I just wanted to give you a preview for this kind of stuff. You should expect that this will have some part of exam 1, maybe something like this, for example. And also maybe a bigger reminder for preparing for exam 1 is you can expect one concept question like this, a few parts. A big part of the exam is stuff like what we're doing here, these kinds of evaluations. But don't forget stuff from section 5.1. You might be asked to say, give an angle and radian measurement, given some information like the radius and the arc length. So you'd be using those formulas from section 5.1. You might be asked to convert something between degrees and radians and those kinds of things. And also every time we did one of these kind of problems here, notice what was really critical for us is knowing this information right here. The fact that secant is 1 over cosine, the fact that cosecant is 1 over sine, and so on. In fact, I made that just a small question itself. Tell me what tangent is, and we really just have to do something like this. Not necessarily literally tangent, but I'm going to ask you what a few of these things are, just to see how well prepared we are on that kind of concept. But really, it's already built into this, because to calculate tangent, you had to know it's sine over cosine. But I think that's my last bit of advice preparing for exam 1. Any last questions or comments at all, folks, before we call it a night? Okay, well, we'll end a minute here this time, a bit early. I guess that probably reduces our balance to 0 just about. We've been going a minute late on a lot of classes. If you have any questions while you're studying for the exam, don't hesitate to reach out at any time. I'll be happy to help. And watch your email when you submit your homework. I'm going to be working on Friday quite a bit, as well as throughout the weekend, getting caught up on Sunday to get your homework graded and send you back that feedback to help you prepare for the exam. But have a great night, folks. We'll see you all next Wednesday.
Thank you.
Yep, take care.